All right, so we're continuing on today in our discussion of oxidizers and reducers. Again, those class 5 materials. Now, based on our conversation and our look at the definitions of oxidation and reduction from Wednesday, one of the kinds of things that I could ask you to do is, given a chemical equation like this, could you identify the oxidizer and the reducer? Could you identify what substance is being oxidized and what substance is being reduced? Now, just to remind you, the primary definitions that we are using for oxidation and reduction have everything to do with the movement of oxygen. Now, in a true chemical sense, that's not the best definition of oxidation and reduction. Oxidation and reduction tend to focus on the movement of electrons, not the movement of oxygen, because not every oxidation reduction reaction involves oxygen. But for the ones that we're concerned about here in hazardous materials, where we're talking usually about oxidizers in terms of their ability to feed fires, oxygen movement is important because ultimately oxidation is going to be the thing that forces something to be able to continue to burn or something to decompose and create elemental oxygen to feed the fire. And our viewpoint of looking at it from an oxygen-based standpoint is warranted because of that. So again, the substance that gains oxygen atoms is said to be oxidized. The substance that gives those oxygens away is the oxidizer or the oxidizing agent. That substance that loses oxygen is said to be reduced. And the thing that catches those oxygens is the reducer. So from that standpoint, what we look at in equations like this is I've got aluminum and potassium perchlorate. And I can see that the aluminum is going to aluminum oxide here. The potassium perchlorate rather, is ditching its oxygen and becoming potassium chloride. So from that standpoint, the aluminum has added oxygens to become aluminum oxide. By definition, that means it has been oxidized. The potassium perchlorate has lost oxygens to become just potassium chloride. So it has been reduced. Since this is the substance that gave away the oxygens, we call it the oxidizing agent or the oxidizer. And since this is the substance that took those oxygens, we call it the reducing agent or the reducer. Now notice, everything that we talked about here is on the left-hand side of the equation. Terms like oxidation and reduction, oxidizer and reducer, they are used to describe reactants in our chemical equation. So never will it be the case where an oxidizer or a reducer comes from the product. The products help us to identify which reactant is oxidized and which reactant is reduced. But those substances are not participating in the movement of the electrons or in the movement of the oxygens. They are the result of those oxygens moving around. It's an important distinction. And it is a distinction that is very difficult for some students to wrap their heads around. I say this primarily thinking of my general chemistry students because when we talk about oxidation and reduction in general chemistry, we talk about it from a much different standpoint. But the whole idea of oxidizers and reducers confuses them very, very easily, just as it will confuse some of you. And I can't tell you the number of times that I've seen products identified as oxidizers or as reducers in their work. So I want you to avoid those same kinds of mistakes. All right, any questions with this example? Okay, so we move away from just simply identifying oxidizers, identifying reducers, defining the terms, to actually looking at classes of oxidizers and classes, ways that we can classify them based upon their relative reactivity. Now, in terms of combustion, we think of oxidizers and fuels. Technically, fuels are the reducers in these reactions, but we don't usually think about fuel or reducer in a combustion reaction. We think about, okay, I've got my oxygen, I've got my fire. I've got the thing that's burning and the thing that helps it continue burning. So fuel and oxidizer tend to be what I focus on from that standpoint when I'm looking at combustion reactions. Just to reiterate, most oxidizers are not flammable on their own. Their primary role is a support role. So if you think about that flame triangle that we looked at, you have heat, fuel, and oxygen, the three legs of the triangle. When all three are present, a fire can form. Absent any of those three, the fire either never starts or puts itself out. So oxidizers are in that support role. They help us provide oxygen. Now, there are some oxidizers that are self-sustaining, meaning that when they break down, they will actually create a fuel and oxygen. And so they kind of self-sustain their own fires. But that's more of a rarity. That's a subclass. We'll talk about those in a little bit. We can rank oxidizers based upon how dangerous they are, what kinds of stability issues they pose. And so we start with our class 1, our weak oxidizers. These are substances that are mildly unstable. And the results of their instability will be that they will slowly produce material, usually oxygen, that can feed a fire. Common examples of these include hydrogen peroxide. Now notice, with the hydrogen peroxide, we are getting a concentration value here. Any concentration value between 8 and 27% hydrogen peroxide is considered a weak oxidizer. Now, this is not the same kind of hydrogen peroxide that you would buy at the drugstore. You go to Walmart or CVS, Walgreens, Dollar General, any place that sells brown bottle hydrogen peroxide that you use as an antiseptic. You get a cut on your leg, pour the hydrogen peroxide in there to clean out the wound, make sure that if there are any bacteria, they get killed in the process. That's only 3%. 3% hydrogen peroxide, sold over the counter, pretty much not dangerous. 8%, the low end of this spectrum, this is the kind of peroxide that you would get maybe at a place that cuts your hair or at a beauty salon, something where they might do some commercial bleaching or bleach your hair. At-home bleaching kits can have up to 8% peroxide solution. On the higher end, it becomes a little bit more difficult to do. A little bit more difficult to get 20 and 25% hydrogen peroxide without having to go through some kind of a chemical supplier. Nitric acid, HNO3. Again, this one has a concentration value as well. Nitric acid is only sold as a solution. There is no such thing as solid or gaseous HNO3 floating around. At concentrations less than 70%, this is considered a weak oxidizer. Also in here, things like ammonium nitrate, very common component of fertilizer. Silver nitrate. At one time, silver was used in a number of processes for photo development. There are some other uses for silver nitrate out there as well. Sodium nitrite. Primary place where we see nitrites are in certain kinds of food. Pink salt, anyone that does their own curing of meats, makes their own bacon, your own jerkies, does any kind of meat pickling processes, like for corned beef. Sodium nitrite, pink salt is the primary component of that. But these are weak oxidizers. Relative danger to us is relatively low if we use them properly. In your class 2, you have your moderate oxidizers. These are substances that will moderately increase the burning rate of certain kinds of combustible materials. These also have the capability to cause spontaneous combustion if in the right fuel to air ratio with the right material. In here, we once again see peroxide, this time in the 28 to 51% range. So now we're definitely getting into laboratory grade kind of stuff. Nitric acid in the 70% and above range. So we're talking really concentrated solutions here now. Calcium hypochlorite. Commercial name for calcium hypochlorite is HTH. This is the kind of stuff that is used for widespread disinfecting for things like municipal water supplies, public pools, public hot tubs. So, you check into a hotel and you go to use the pool in the hotel, there's a good chance that HTH was used to clean and disinfect that pool so that you're not taking in 500 other people's bacteria when you go swimming. Potassium permanganate. Really cool compound, potassium permanganate. It is a really dark purple color, but it is a very, very strong oxidizer for certain kinds of situations. Whenever we use potassium permanganate here in our laboratories, we actually have to react any excess materials to get it out of this oxidizing form so it doesn't ruin the pipes. Sodium peroxide, Na2O2. You'll actually get a chance to work with a little bit of this stuff when you do your oxidizers lab. Just a small amount just to see how it reacts when it decomposes. Your strong oxidizers, class 3, these are substances that will severely increase the burning rate for combustible materials. You can also find among these things that will undergo self-sustained decomposition reactions when they are catalyzed or when they are heated. So this last bit here pertains especially to these compounds here at the bottom. Your chlorate compounds, when they undergo a decomposition process, when they just get heated up, they will start to create massive amounts of oxygen and heat. And the cool thing about those is these are the substances that are at the heart of fireworks. A lot of them are, at least, as an oxidizer, because they can go into the firework as a solid material. As the rocket's being shot up into the sky, it's generating a ton of heat. The heat decomposes the chlorates, which create the oxygen, which allow the explosion to happen, and we see the firework as a result. Depending upon what ion is attached to the chlorates, we can actually get different kinds of color effects as a result. So along with the chlorate compounds and the perchlorate compounds, we also see hydrogen peroxide in really high concentrations now, 52 to 91%. And we also see super high concentrations of calcium hypochlorite, HCH, at greater than 50%. The last class 4 here, these are your explosive materials. These will undergo explosive reactions when they are catalyzed, when they are heated, when they're exposed to shock or friction. So in here, you're seeing extremely high concentrations of hydrogen peroxide. This is the kind of hydrogen peroxide that might be taken as part of a propulsion unit for things like going into outer space. To do some of the chemical reactions that are required up in those in space. Perchloric acid, again, in very high concentrations. And we also see combinations of other ions. So remember from the class 1 ammonium compounds, we had ammonium nitrate. Well, when we pair ammonium with chlorate, so we had something that was with the weaks and something that was with the strongs. Now we've got an explosive material in the ammonium chlorate. Same thing with the ammonium permanganate. I took 2 ions that have oxidizing power to them, combine them together. Their forces of oxidation multiply. They become much, much stronger as a result. So before we move on to those organic peroxides, let's take a moment here and look at, because we're already on YouTube. What we have in this test tube is a simple compound. This is potassium chlorate. Potassium chlorate, as you saw a couple of slides ago, is a strong oxidizer. With those strong oxidizers, as I mentioned before, those strong oxidizers will generate oxygen when they are heated. And potassium chlorate is certainly no exception to that rule. So what we're going to do is they are going to heat potassium perchlorate, or excuse me, I keep saying that, the potassium chlorate get it into a molten state. In that molten state, they'll start to decompose, create lots of fresh oxygen, lots of heat because it's molten. And then they're going to throw a gummy bear in there. And the gummy bear is going to spontaneously ignite inside of the test tube because we now have all the conditions that are necessary for a fire.
Welcome to C4 Chemistry. Gummy bear is a sugar-rich candy. It could readily oxidize under oxygen-rich environment. Bunsen flame hits the tube evenly by torching it at different angles. Pure potassium chloride melts at 356 degrees Celsius with decomposition. Molten potassium chloride decomposes to produce oxygen. It turns to a colorless or milky liquid and provides an oxygen-rich environment. When the chloride powder is melted, choose a piece of gummy bear which is ready to be sacrificed. Judgment Day of the gummy bear has come. Temperature of the mixture provides sufficient activation energy, and the gummy bear vigorously bursts into flame. One can clearly see the liquid flame derives from potassium ion.
All right, so the combustion reaction that we saw there was one you've seen many, many times. Gummy bears are sugar and gelatin for the most part. And all that really happened there is, well, the sugar burn. Now, the other things that you saw there were as a result of the byproducts. And the byproduct in this particular case was potassium. Not potassium metal, but potassium ion. Now, potassium ions, when they are excited, when they are under a lot of heat stress, their electrons start jumping up all over the place. And when they come back down to normal, they let off some light. And a particular characteristic color for potassium is purple, which is why the sparks that come off of that are purple in color. Now, this particular type of electronic excitation reaction is actually at the very heart of, again, I've been referencing fireworks in a number of cases here. This is what happens in fireworks, essentially. The heat that is generated by the fireworks get used to excite the metal ions that are in the firework, and that's what gives the firework their color. And depending upon what metal ions you mix into your mixture, you'll get different colors. But more about that later. Let's talk now about organic peroxides. Now, a peroxide in general is a compound that contains this particular oxygen to oxygen single bond. Now, we know from our discussions in chapters 4 and 5, oxygen likes to make double bonds with itself. You think about how oxygen is put together, if you look at how the electrons are kind of distributed, oxygen likes to make bonds with itself that are double bonds. While oxygen certainly meets its octet for all of these compounds, it's not a stability issue necessarily from an octet rule standpoint, it is a stability issue from the standpoint of that oxygen to oxygen single bond is relatively weak. And since that oxygen to oxygen bond is relatively weak, it makes the compound unstable and the substance that contains that compound, that contains that linkage, very reactive. Now, we talked at length about hydrogen peroxide, which contains hydrogens attached to both ends of that oxygen to oxygen single bond linkage. These substances, hydrogen peroxide, is not considered an organic peroxide. It is a peroxide. It is unstable. We saw how hydrogen peroxide was represented in all four of the classes, depending upon its concentration. But in order to be an organic peroxide, I need to have a carbon-containing group on one or both sides of that oxygen to oxygen linkage. That is what distinguishes an organic peroxide from another peroxide. How do we get organic peroxides? We usually get them through an oxidation process of their own. The oxidation process that we are speaking of primarily here is something called taking an ether. An ether has an oxygen linkage inside of an organic compound where I've basically got an oxygen right in the middle of a bunch of carbons. It could be. It could be. That is not something I'm familiar with, but it could be. Yeah, manufacturers usually don't throw around words like that incorrectly, so chances are pretty good that it is. I just wouldn't know which ether it is. There are lots of different ethers. Most ethers, you do have to watch out for. A number of ethers are on the list of carcinogens. So that's where I would be hesitant that we're talking about the same thing, but it could be. There are lots of different ethers out there. But the most common ones, dimethyl ether, the one that's shown on the screen, diethyl ether, which was used as a solvent, still is for a number of different organic reactions. Those are on the bad list. And so you got to be really careful when you work with them. At any rate, when we react these ethers with oxygen, they create organic peroxides. And those organic peroxides can then decompose. And when they do decompose, the dangerous part about them is that they form their own fuels and an oxidizer to go with them. So we get some kind of a breakage in the linkage here. The molecule rearranges itself. We end up getting an alcohol. Alcohols are flammable. And we get oxygen gas, which can be used to burn said alcohol. And so this is why organic peroxides get their own subclass by the DOT. So we talked about at the very beginning here, the two different types of placards for the DOT. The plain old oxidizers, which is class 5.1. And then there's the organic peroxides, class 5.2. The reason for the separation is because of this. These organic peroxides have a special danger associated with them because under stress, they will form their own fuel and their own oxidizer, which means they can basically spontaneously combust if the temperature is hot enough. All right, let's talk about another common oxidizer, oxygen. Now, oxygen is not in class 5. It is actually in class 2 because it is a gas. But other than that little difference in number, oxygen has all the earmarks of a oxidizer. It's got a yellow placard. It's got the flaming O pictogram. It just happens to be a gas, and so we have to classify it as a gas instead of as an oxidizer. It exists as O2 in its natural state. We've drawn its new structure before. It naturally forms a double bond with itself. And so that is how it stabilizes itself for use and to help it meet its own octet. It itself is not a flammable material. It is colorless and odorless. It is the most common oxidizer that we find in the air. In fact, it's of the substances that we have that are oxidizers, this is the most common. And this is also the most common byproduct for the other oxidizers that aren't oxygen. You notice that almost all of the ones that we talked about had oxygen included in some kind of way. On its own, it comprises about 21% of your air, with nitrogen making up the majority of the rest, 78%, and carbon dioxide and the others making up that little 1%. As an oxidizer, oxygen is actually not very good. Here is a list of common oxidizers. And you see on this list of common oxidizers, oxygen is way down here. It's one of the weaker ones. That's actually a good thing. We know a number of these substances in the presence of other materials will react almost readily. So the fact that the thing that we are walking around in that makes up 21% of our air roughly doesn't immediately start oxidizing us and breaking us down and causing chemical reactions with us as we are walking through it, it's actually a pretty good thing for us. There are other substances on here, and those substances will do some damage to you based on their concentration just by interacting with them. Nitric acid, for example. Nitric acid, you get some on your hands, by accident or otherwise, it's going to turn your hands yellow. And not just, turns it like a washable marker, you wash it off, it's gone in a day. Your hand's going to be yellow for probably about a week, depending upon the concentration. In higher concentrations, you have to actually wait until your skin basically regenerates itself to fully get rid of the yellow skin. And that's not to say of anything about the acid part of it. That's just the oxidation part of it. If you have high concentrations of nitric acid on your skin, it's going to start burning your skin too, because that's the corrosive part. So nitric acid kind of has a nasty side tone to it. It's a corrosive and an oxidizer. It eats away your skin and reacts with your skin to cause it to turn colors. Nasty stuff. Now, luckily for us, that effect usually doesn't take on until we're at some relatively high concentrations of nitric acid. But nonetheless, that's what it does. And so some of these substances, you got to be really, really careful about. Why are we so concerned with ozone? Well, as we said before, ozone in the upper atmosphere is a good thing. blocks out ultraviolet light, blocks out a lot of the cosmic energy that comes from the sun, stuff that we don't want coming through and down to us in the lower atmosphere. Down here, ozone's kind of a problem. You breathe it in, it burns, kind of smells funny. Well, that's because it's reactive. O3 is not the natural form of oxygen. O2 is. And so when you encounter O3, it's going to want to react to get back to O2, which is where it's more comfortable. And part of that process is that it's going to take some stuff from you. It's going to strip you of some of your electrons. So even though it's abundant, even though its reactions are common, it's not a weak or it's not a very strong oxidizer, and that's actually okay. That's good for us. If we encounter some of these other things, though, we know that they're going to have impacts on our body. Because more than just exchanging oxygen with us, we have to think about what happens when your body cells start losing electrons. Weird things can happen depending upon where those electrons got stolen from. We'll end today by talking about hydrogen peroxide. Hydrogen peroxide is well known. It is the substance that is in all 4 of our classes of oxidizers. Which class it is in depends upon its concentration. Just as kind of a field study here, we'll mention that depending upon the concentration, it has different applications and uses for us. So, for example, at the 3% level, this is the antiseptic level. This is the stuff that you can buy, and when you fell off your bike when you were a kid and your mom or your dad took you into the bathroom and put hydrogen peroxide on your skin to clean out the wound and you screamed because it hurt, this is what they used. At the 6% level, you can see this as a bleaching agent for hair. At the 30% level, you can see it as a bleaching agent for consumer goods. Things like cotton, wool, leather, paper. At greater than 90% level, this is again what I was talking about. You can find this used as a propulsion agent. This is your rocket fuel. And makes a pretty good rocket fuel because at that concentration, it's in the liquid phase. We can compress it pretty easily, store it at relatively low temperatures, and it'll survive outer space. All right, this is where we're going to stop for today. On Monday, we'll look a little bit more at hydrogen peroxide, and then we'll take a look at some other very common oxidizers. Should help us to finish out the unit or at least come close. Have a great weekend.